Okay, let's get started. So today's recitation is all about debugging Malloc lab. So hopefully you've all started Malloc lab. It's due Thursday. So if you haven't started, you should start like immediately after recitation ends, because it's due very soon. How's it been going for everyone? Okay? Making progress? Is anyone done?
Points.
Oh, that you're just not going to submit anything more? Okay. Well, today we're going to talk about debugging it to make it better if you're having issues. So maybe you've seen some stuff like this before. So you run the driver and you get back this message, garbled bytes. So some people have seen this. I know because it showed up on the email list at least once. What does that mean, garbled bytes? So the way the driver works is that as it's testing out your allocations in freeze, it's writing random bytes into this memory that you allocate. That's the default setting, is that it'll do this. And then it checks to make sure that those random bytes are the same when it goes to free it or whatever. So what that's checking is that your implementation does not write to any of the memory that you've given to the user, that you've allocated for the user. So if the user requests, if the user does an allocation of 16 bytes and you give them back a pointer, you better not touch anything in the 16 bytes following that pointer, because that's their memory to deal with. You can play around with your stuff on the header and footer on either side of it, but don't write inside of it until it's freed. And so if you're getting the garbled byte message, that means that you have corrupted the payload with something you've done. And so this, this could be caused by all sorts of things. Maybe you just have a miscalculation in your offsets and you're just slightly overshooting the bounds of it in either direction. Maybe you're not keeping track of the lists of free blocks or allocated blocks correctly, and you're actually just like allocating more space halfway through the middle of it or something. But that's what that message means if you see it. And another message you might see is out of memory. So out of memory means you've allocated way more heap space than you should have. None of the tests should cause out of memory if you have a reasonably implemented malloc. So what that probably means is that you're just like completely not keeping track of your blocks, or that you're just extending your heap by an unreasonable amount way too often. So I mean, if you're getting the out of memory error, you would be getting probably a 0 on util anyway. So the fact that it shows up as an error rather than a 0 just helps you kind of see what's going on. Okay, so you might get those, but other times what you'll get might just look something more like segmentation fault. Nothing more. No helpful message as to what it is, just something's wrong. So, I mean, you've seen that. I'm sure someone has seen that, right? Segmentation fault. So this is sort of the difficulty of this lab, is things might go wrong, and it can be hard to figure out why they went wrong. Because it's a very manual, low-level maintenance of this data structure that you've created, and this data structure has these invariants, which might be things that you've decided. There's not just one malloc implementation that we're asking you to implement. You sort of got to pick certain parts and pieces, and you're trying to put them all together. And if if you're not respecting one of those invariants somewhere, then something like this will happen, and you have to figure out where it went wrong. So of course, one thing that you can do, as always, is GDB. So the nice thing about this lab, maybe you realized this in the previous labs, is in bomb lab and in attack lab, you were running GDB on something where you didn't have the source code. And so when you ran GDB, you were mostly just looking at assembly, and you're manually inspecting what was going through the registers and maybe some memory locations like the stack. But now you're actually debugging something where you have the source code and you compiled it. And in the make file is the -g flag, which means that all of that information is stored in the executable for debugging purposes. And so when you run GDB on mDriver, you'll be able to see exactly what line of the source code it actually failed on. And you can even print out the variables. So if you have the variable BP and the line seg and the code seg fault's on a line that contains BP, if you do print BP, it tells you the current value of BP, just like you can print out registers. So if you haven't been using that, that is something that might be useful to you to find out exactly where it's going wrong. But one thing that you need to note is that it's not necessarily the line that it seg faulted on that's the line that's wrong. It could be that something went wrong much earlier, and it's only once you get 70 lines later that it actually manifests itself as trying to access something that you're not allowed to access. So the question is, how do we go about figuring out that earliest point that things went wrong? Because some of these traces are very long, and you don't want to step through it step by step. Doing it in GDB one step at a time, and then on paper with a pencil right next to it, and go 13,000 lines into the trace, and then say, that's where it went wrong. That'd take way too long. So you might think, the first thing you might think is, well, I'll just print out the whole heap before and after I do every allocation, before and after I do every free, and then I'll just look through them and find the one where it looks wrong. You'll get a lot of output this way, like way more than is useful in any of the large traces. On a smaller trace, maybe this would work, but if you're failing the larger traces, this is going to be very difficult because it'll be thousands and thousands of lines of pointers and stuff. And so good luck trying to figure out where it went wrong efficiently doing that. So this is where the heap checker comes in. So the heap checker is that that part of the assignment that's worth 10 points that you shouldn't just wait till the end to do. Some people view the heap checker as something that they just write at the end once they have a working malloc, but that's the wrong way to do it. You should do the heap checker before you write the malloc, because the heap checker is going to help you debug. So the point of the heap checker, I think I emphasized this last week too. The point of the heap checker is to check all of the invariants of your heap. And so if you have this heap checker written before you actually write your malloc implementation, then you can run your heap checker every time where the invariants are supposed to hold, and then it'll fail the first time that they don't, if you're having an error. So one thing that's important to note is that you can't just call the heap checker after every line, because say you're halfway through coalescing, and you've pointed one guy to the guy who he's pointing to now, and you haven't gone the other way yet, or something like that, or you're modifying your free list. And you're halfway through adjusting your linked list. Calling the heap checker there, of course, it's going to fail. So you have to be careful that you're calling your heap checker only in locations where the heap checker is actually supposed to pass, where that all of the invariants should hold at this point. But once you've identified those points, it's good to call the heap checker as often as possible so that you can identify the first place where something goes wrong. So once you've settled on a design, because your heap checker is going to depend on your design, whatever invariants you choose. If you're choosing to do something with, if you decide that you want to do 32-byte headers, I don't know why you would decide that, but maybe you're going to decide that might influence your heap checker, and it would be different than if you're doing 4-byte headers. Or if you decide that you want to only do singly linked lists instead of doubly linked lists, obviously that's going to affect your heap checker, because with a doubly linked list, you want to check that all the backwards pointing links are correct. If you're doing a singly linked list, that's not something you can check because they don't exist. So once you've picked a design, as you're working on this implementation, you're probably starting with the MM textbook. I'm sure most of you just copy and pasted MM textbook into mm.c as to start. That's a reasonable thing to do because that's a working implementation of malloc. It doesn't get any points because doesn't have good enough performance, but it works. And so that's a good thing to start with, because then you just have to make it better. You don't actually have to write a working malloc implementation from scratch. So what you're doing is you start with the implicit, and then you're going to the explicit, and then you're going to the segregated lists. And each time you're adding new invariants to your heap checker, or maybe some of the old ones are going away, depending on exactly how you're designing it. But each time, you've come up with the design, you should update your heap checker, or initially write the heap checker, if you don't have one yet, to check all of those invariants of that design. And then as you implement that new design, your heap checker can be running on it on all of the traces and tell you immediately if you've made a mistake. Tell you if you implemented something that doesn't actually maintain those invariants. And then your heap checker is going to change with your code. As you update from implicit to explicit, you update the heap checker. This is sort of maybe the reason why some people think, oh, I'll just write the heap checker at the end, because then they don't have to update it. But the cost of that is that you'll probably spend a lot more time debugging than you would have just updating the heap checker when you do those transitions. So the heap checker, what it really should be is it needs to accept exactly the valid heaps and reject everything else. And you want to call it as often as possible everywhere where the heap is going to be well formed. But of course you don't want it running running all the time. So this is what we talked about last week. It's good to be able to turn it off, because especially when you want to see how fast your implementation is, or if your implementation is correct, you're not having any correctness issues, and you just want to be running in, and the heap checker is taking forever, because it's a linear pass through the heap. Then you can define a macro and use a macro to turn it off. So here's another example of it, slightly different from the way I did it. This macro actually takes the heap checker and prints out the function it's about to be called from before calling it. And it still gives it the line number so that the heap checker itself can print that out. So does everyone understand this macro of how to turn the heap checker on and off? How to write something like that yourself? And that way you don't have to manually comment out every call to the heap checker to turn it off. So what are some of the invariants you should test with your heap checker? So it's good to check that the header and footer match. If they don't match, that's a problem. You want to check that the payload area is aligned. So we have this requirement that you have this 8-byte alignment. So you want to check that every payload in your heap is aligned to 8 bytes. Then you have sort of the linked lists of blocks. So what do you want to check there? You want to check that the next and previous pointers are consistent. So now you've got some blocks. This guy has a next, and this guy has a previous. And if you follow next and then previous, you better get back to where you started. Because if previous points to some third guy down here, that's a problem. That's not a well-formed doubly linked list. So you want to check that the next and the previous are correct. And that, if you go back and then forward, same thing, that you get back to the guy you started. And at some point, these end with whatever design you've come up with for knowing that you're at the end of the free list, unless maybe you have a cyclic list. So maybe you've come up with a design where your list is actually cyclic. Then you'd be going around, and you'd have to have some way of knowing that you're going around. Otherwise, you're going to want to check that it's not cyclic, and the next slide we'll talk about that a little bit. So some other things, you want to make sure that your free list doesn't contain any allocated blocks. So if you traverse your free list and you find something that's allocated, that's bad, of course, because then you'll potentially be giving allocated memory away when someone calls malloc, and that would easily become a garbled bytes error message, as new random bytes are written to it, and then the old ones won't match. You want to check that all of the free blocks are in the free list. So you'll be doing a pass through the heap, just as you've just got this big flat heap, with some things are free and some things are allocated and whatever. And then, within it, there's all of these arrows pointing around in different directions, that form this list that are skipping over these allocated blocks. Maybe these are just the free guys here, and we're skipping over some allocated blocks. you want to make sure that if you just go straight through the entire heap, just as a flat structure, using your headers and footers to find things, and if you go through the linked list using your next and previous pointers, that if you count up the free blocks either way, you get the same amount. There shouldn't be any, there shouldn't be like a free block sitting over here that's just not part of your free list. Because if that happens, then, then you're losing space, and that's going to hurt you in your util. That one might actually, something like that could be, you might pass all the traces with that. This is somewhere where the heap checker is actually even going to help you not just know it's going to be correct in terms of passing the traces, but correct in terms of actually, recovering all of the free memory it should. Because if you just forget about a free block, as long as you never do anything with that chunk of the heap, it doesn't hurt you in terms of correctness to just never touch it again. But it does hurt you in terms of performance, because that's wasted memory. If someone tries to allocate memory, you're going to treat it like it's allocated even though it's not. So that's another thing to check. Free blocks in the heap. So say you have two free blocks next to each other. Unless you're doing deferred coalescing, that would be a problem. So you made some decision about when do you do coalescing. Do you just coalesce immediately every time you are able to coalesce, or do you wait until some point and then do coalescing then, potentially on multiple things all at once? So depending on what you've decided there, which invariant you've chosen, it may or may not be an issue to have two free blocks next to each other in the heap. And they might not be next to each other in the free list. Maybe maybe this guy is actually connected up to this guy in the free list. But in the heap, if they're next to each other, then they can be coalesced. And so depending on your choices for when coalescing should happen, you should check that the coalescing has actually happened if you expect it to. And then segregated lists. So this is something like as you update your implementation, you're updating your heap checker. Once you go to segregated lists, you'll update your heap checker to say that each segregated list, so each one, it becomes its own free list. We've got a bunch of free lists. You want to check that each of these lists contains only blocks in whatever size class it's supposed to be. So maybe you've said that this segregated list is for blocks that are less than or equal to 8 bytes. And so then you would go through this free list and check that every guy is at most 8 bytes. And if it's anything else, then that's a problem. This is another one where it might not show up in correctness. Say you had a 16-byte guy in here. Well, you can still use him for anything that would need less than or equals to 8, but that's going to decrease your util possibly, because you won't be able to find the right size block efficiently. And then there's the whole heap level invariance. So you've got this prologue and epilogue blocks on either end. You want to make sure that they're in the right location, that they're there, that their fields are correct, so that they can work as the special boundaries as we traverse the heap, so that we know that we're at the ends and don't just go off into the memory that we don't have. Because you'll notice that you'll get a seg fault if you just start trying to dereference stuff beyond the edge of the heap. Because that memory does not belong to you. And then you want to also, you want to make sure that all blocks stay between the heap boundaries. If you're overriding the edges of the heap, that's probably going to end up being a seg fault. It's certainly not correct if it works. So that's something that you want to check, because that can cause all sorts of problems. And then you might have your own invariance. So at some point, maybe you decided that your free list is going to be stored in address order. Maybe you decided that your free list is just going to be stored in size order. Maybe it's sorted by to you might have come up with just some other invariance that you're going to use for whatever reason, to improve your throughput or your util. And so you should make sure that you check all of those, whatever they are. And this is a non-exhaustive list of invariants. There's all sorts of other things. Are there other invariants that people are checking with their heap checker, or think they need to check that aren't covered by anything on this list? No one has anything. You can come up with more, depending on maybe you're doing some really fancy implementation, you would probably have more invariants to check. So yeah, so then cyclic free list. So I mentioned that there'd be more on this. So one of the things that's good to check is that your free list has no cycles. And so I actually have a story about this. This was relevant to me when I took the class because I wasn't checking that my free list had no cycles. So I was having a trace and it was taking a really, really long time. Like I would run this trace and it would just take forever and I'd just have to like control C out of it. It just wouldn't finish. I didn't know why. So I didn't have cycle detection as one of my invariants in my heap checker. And so the heap checker wasn't failing. I decided that I would I'll just print out some information about, the heap nodes, the different, the free list. I was going to print out information about the things in the free list. But it was way too much to actually read through on the terminal. So I decided, well, I'll just pipe it to a file then. And so now I'm piping stuff to a file. And I don't know it, but my free list is cyclic. And I'm printing out information for every node into this file. Does anyone have any idea what might happen if you're printing out information about every node of a cyclic free list into a file?
Infinite loop.
Yes, it infinite looped. And I was made aware of that infinite loop when I received a message that I had exceeded my Andrew disk quota. And I checked and it was over a gigabyte of output. Because it had just looped through this list over and over, printing out stuff for every node. It's not a very efficient way of debugging things. I sat there for quite a while waiting for it to write this file, trying to figure out what was going on. So, the issue was that I wasn't checking this invariant, that my free list didn't have any cycles. And it did have cycles, and so that was causing problems for me. And if I had had that in my heap checker, I would have received a message the first time it went around the cycle that there was a cycle, and I wouldn't have printed out the thing, several thousand times into this file. So this is an algorithm here. This is called the hare and tortoise algorithm. It's also known as Floyd's algorithm. And the point of this algorithm is to detect cycles in linked lists. And it does it in linear time. It's a relatively efficient implementation of it. So the idea is that, we have some linked list. So we only need to, we're just considering arrows in one direction here. So of course, there's the arrows in the other direction. If they cohere, if we have all of the forward and back arrows matching each other, then checking that one direction is not cyclic, checks both. But you have to be careful about what order you check them in. If you're going to just go around the whole thing checking forwards and backwards and there is a cycle, you might be going around forever. So you can sort of play around with different ways of making sure that it always terminates. So say we have some linked list and there's a cycle in it. So this guy points to this guy. So there's actually two guys going here. So if we follow this linked list, we'd go around here and then we just loop through these three over and over and over forever. This is sort of the problem that I was having. So the way this algorithm works is you have two pointers. One is the hare and one is the tortoise. And you start them both off at the first guy in the list. And what happens, the way you update, so you take at each time, it's a loop, and each time you do this operation where what happens is the hare moves forward by 2, and the tortoise moves forward by 1. So in the first step, we'd say the hare goes forward 2, so he ends up here. And actually, let me just write them on the inside. So the hare ends up here, and the tortoise moves forward by 1. So he ends up here. And then we keep doing that. So the hare moves forward by 2, tortoise moves forward by 1. And if the linked list is actually not cyclic, so if it just ended here, then in the next step we'd try to move the hare forward by 2 and we'd say, we've hit the end of the list. And then we know it's not a cycle. If the hare actually reaches something that's the end, we're done, right? The interesting case is when there is a cycle, because then there is no end to reach. So what happens is, so here we'll move the hare forward by 2, so that would bring him back here, and the tortoise was there, so he moves here too. What happens is that if there's a cycle, then eventually they'll end up on the same spot.
Does it have to be in the first cycle itself? Or like it could be after like it goes through 4 cycles, like the age?
It will always actually be in the tortoise's first time through the cycle. The hare might run through the cycle multiple times depending on how long the chain leading up to it is, because the hare's moving twice as fast. If the cycle's really small and the chain is really long. But what you actually know is that it's going to be the first time the tortoise makes it into the cycle, it's going to hit the hare. And it's sort of, this isn't an algorithms class, so this isn't something that's on your exam or anything. But sort of the thing you know is that when the tortoise enters the cycle, the hare is somewhere inside the cycle, because the hare is ahead of the tortoise. And so what you know is that the tortoise is going to move one per time, the hare's moving 2 per time. So the hare is getting closer to the tortoise by 1 every step. So that means that even if the hare is like just past where the tortoise was, the number of steps that it will take them to catch up to each other is at most the length of the cycle.
So one behind the tortoise.
So if he's one behind the tortoise, that's actually optional, because he's going to move forward by 2, and the tortoise is going to move forward by 1, and then they'll hit each other right away. Yeah. But you do know that this is actually, since the tortoise is moving forward by 1 every time, it's going to be, the number of steps it takes is at most the length of the whole thing, the number of unique nodes in this list. And so yeah, so if the hare reaches the end, you're good. There is an end. Otherwise, they will hit each other, because the hare is getting close to the tortoise by 1 once they're both in a cycle every time. And so eventually they hit exactly. And so, once that happens, then you can print out an error and you don't loop forever and end up with a gigabyte of debug output exceeding your Andrew quota and all sorts of nonsense like that. This is the value of the heap checker. It will save you time, it will save you frustration. It will help you write a correct implementation. And it's worth 10 points. So, you have to do it sometime, you might as well do it now. Okay, so some other things to watch for. So make sure that you're initializing everything correctly. So one of the things that people have seen is they'll run just the driver for just correctness, and everything passes. And then they run it for performance, and then it starts failing. They say, okay, what went wrong? It was correct, and now it's not. So the difference is that when you run it for correctness, it's running everything just once, and you run it for performance, it does multiple runs. And so if you're having that issue, what it almost certainly is that you're not reinitializing global values in between runs. So MM init initializes everything. It should reinitialize any global values you have every time it runs, because otherwise those values will persist across multiple runs, and it's probably invalid for you to start with these global values that were determined by a previous run as the new initial values. So make sure that you're doing that, especially if you see like it's passing with the correctness flag but not with the performance flag. Okay, and then there's the good old tool valgrind. Has everyone seen valgrind? We can run it just for the sake of the video in case there's people who haven't. So there's a great tool. There's a great tool called valgrind. So I might be running my so I have a trace, and I can run it. It's taking forever. What's this one take so long? Okay, but maybe okay, my util was pretty bad, and I want information about sort of how much memory was sitting around at the end, wasted. So valgrind is a tool that can be used for finding memory leaks and invalid memory accesses. Maybe I'm having some memory-related error. So if I run the program through valgrind, what's going on? So I can run the program through valgrind, and let's see, what it will tell me. Tell me that at exit I had 525,000 bytes in use. I did 12 allocations, I did 8 frees. Okay, let's see. But it looks like I didn't leak any blocks in the middle. So I didn't leak any blocks in the middle. I just had stuff that was unfreed at the end. And I can run it with this extra flag to see more, or I can run it with -v. -v will give me more information about things that went wrong. So if you're getting sort of memory-related errors, this example is just the textbook implementation, so it doesn't have any issues. But maybe you're having issues with memory getting used in ways that you don't understand. Valgrind will sometimes give you information about what's going on. Let's see. So one thing about asking for help, because you might want to go to office hours at some point if you get stuck. That's a good thing to do. But remember that there's 500 different designs of these allocators that all of you are coming up with, and so if we just we can't just look at it and know what's wrong immediately, because we don't know exactly what your particular design is. It's not like previous labs where you all have one particular thing that you're trying to do. There's this end goal, but so many different ways to get to it. Things that would be correct to get to it in one way will not be correct to get to it in others. So when you are stuck, a good thing to do is to sort of work through figuring out exactly what the detailed understanding of the problem is. Even if you don't know what the problem itself is, at least sort of where in the trace does it fail? Which traces does it fail on? That's an even better place to start. Which traces does it fail on? Where in the trace does it fail? And then, as much as you can, to figure out what did you expect to happen and what actually happened there instead. Because a lot of the time, if you can figure that out, that points, that gives you huge amounts of information into what actually went wrong. Just knowing that it seg faults is not particularly helpful. Knowing where it seg faulted and what it was trying to do and what you thought was going to happen and what actually happened instead, that's much more helpful. Because the seg fault could be in all sorts of different parts of your code. And you can use GDB, you can use your heap checker as tools to help you narrow in on where this problem was and what went wrong. And those are good things to do. Those might actually help you figure out the error yourself, even before you have to ask. But certainly, if you do have struggles, don't hesitate to come to office hours, and we'll try to help you out as much as we can. So here's a good response versus a bad one. It seg faults. Okay, that's hard for us to help you if that's all we know. Versus, if it's big allocations mess up your coalescing somehow. That helps us a lot more in terms of figuring out where it went wrong. So a couple more tips in terms of just not writing code with errors in the first place. It's hard to get it all right the first time. I don't think anyone has a working, perfect, full credit Malloc implementation the first time they type in make. I'd be impressed if anyone could. You'll probably make mistakes, but the good thing is it's good to adopt practices that reduce the number of mistakes you make from the outset, so that you don't even have to do debugging. So sort of like the heap checker helps make debugging more efficient. Good planning reduces the amount of debugging you have to do. But all of these, ultimately make your life a lot easier. So some good things to do is to think about what each function is going to do before you just start writing it. These functions are doing things that are fine-grained enough that you don't want to just like start writing it and hope it works out, because just getting like slightly off in terms of what byte you're looking at and playing with is going to completely break everything in many cases. So you want to make sure you have a very clear idea of what you're doing. In many cases, drawing pictures is helpful, sort of like even very basic stuff like this, just to sort of understand where are things and how are they connected, and what information am I keeping track of, that stores those relations between the different parts of the heap. Make sure you're considering the edge cases. So you've always got these edge cases of like the very front of the heap and the end of the heap, and the front of a list and the end of a list, and you've got the prologue and epilogue blocks to sort of deal with those edge cases for you in the case of the heap. Those are designed so that you just treat it like it's not an edge, and things work anyway because of the values stored in those. You should similarly think about how are you going to deal with the beginning and the end of your free list so that you can get things to work in a clean way there. Writing pseudocode is not a bad idea. Just sort of mapping out at a high level, I want to do this, and then I want to do this, and I want to do this, and then filling it in with the details of the macros and the actual byte level manipulations after you have sort of the outline. And you want to document your code as you write it, because you're going to have to document it anyway. This is like the heap checker. You have to do it anyway. It's part of the assignment. You might as well do it while you're writing it, so that you can go back and as you're debugging it saying, hey, wait, I said that this was supposed to happen. I had this invariant, and I'm not keeping that invariant. That's where my problem is. Rather than trying to, spending all that time debugging and then after the fact writing down the invariant that you forgot about. This is a good lab in terms of like those function header comments and stuff. You want to make sure you're writing the invariants that you're expecting. More than in the other labs, there are invariants here that you're expecting free lists to have certain structure, and you're expecting everything to be arranged in a certain way. And so your functions, should be documented with what they're expecting in terms of that, and what they're guaranteeing in terms of the output. Are they guaranteeing that the invariants are maintained, or is this a function that's just doing part of an operation and it's relying on something else to finish it off and restore, the full heap invariance that you have. Okay, and also make sure you write that program header comment. There are still some people on Shell Lab who are missing that. Again, on this lab, there's so many different ways to do it. It's a really good idea because it is worth style points, but also a good idea for the sake of, if you went back and looked at your Malloc lab, and just in general, anytime you're writing code that other people are going to look at, or you're going to look at some point in the future once you've forgotten all of the stuff that you were thinking about when you wrote it, it's good to have a summary of what it is and how it works. Like in this Malloc lab, there's so many things about all these choices you made. How are you doing your free list? How are you doing coalescing? What are if you have segregated lists, how do you organize them? How are you doing headers and footers? All of that stuff is something that to just have a summary of that at the top, so that anyone who's going to read through the files sort of knows the big picture, what's going on, without needing to understand every detail of it. You'll be able to look through it and know what's going on, and that's a good thing to have, and is worth a couple of style points, and should help you just to be able to, if you can state all of your your design decisions, it's good for you to think about those and make sure you're very clear on what you're doing. Another thing. So version control or some sort of backup. So you may have noticed on this lab you come up with some great optimization, you implement it, and your points go way down. Like your optimization isn't an optimization at all, it just completely trashes your throughput or something. And at that point you're like, well, I just want to go back to what I had. That was so much better. So, of course, every time you hit a point where it's correct and it's working, or you've made some progress in debugging, you want to have some sort of backup that you can get to later if you mess up and want to just say, go back. A couple ways you can do this. If you're familiar with version control, if you are familiar with Git or SVN or whatever, and you want to use that, that's a perfectly great way of doing that. If you haven't used version control before, and you're not interested in complicating this lab with trying to learn version control on top of trying to implement Malloc, just make copies of the files. Make unique copies of the files, name version, whatever, as you go. And then, any time when you want to back up and get to a previous version, you can just restore that. And there's this great command, ln. So what ln does is it creates links. So this is the equivalent, links on Windows, they're called shortcuts. All this does is it says this file is actually just pointing off to some other file. And so what you can do if you want is you can actually make mm.c a link rather than a real file. And so you have all of your different copies, and then you can just link mm.c to whichever copy you want to be compiling right now. And so you can read the man page about how to make these links. It's essentially, you give it the name of the link and the name of the thing that it's supposed to point to, and it links them up. So that that's an easy way to switch between the versions rather than like trying to do a copy and paste into mm.c all the time. Which if you get the argument order wrong and you're copying and pasting, disaster. You've just overwritten whatever version you wanted. So be careful with this. Also, of course, Autolab can serve as a version control system. Every time you submit to Autolab, that's a submission that you can download again. There's an option to download old submissions. So if you need to go back to that point and for whatever reason you don't have a local copy, you can always download from Autolab. A couple things, tweaking parameters. So you might have noticed that there's this chunk size macro, and it's just like this random 1 shifted by 12, I think, is the default. And who knows where that came from, is probably not optimal for your allocator. That's something that at the end, or near the end, you want to just put in different values for that and figure out which one improves your performance by the most. Because that's really easy to just change a number a couple of times and then pick the best one. You can pick up a couple of points pretty much for free that way. But in order to be able to do stuff like that, you need to make sure that your code is properly modular. The reason we want to put it in a macro up at the top is so that in the end, when we want to just play with different version values for it, we can just replace it in one spot, and we don't have to actually look through and find all of the places we used it. Because if we have to do that and we miss one, then it's probably going to break everything. It's slow, and we'll lose style points for having magic numbers. And so, you should make sure that all of your special parameters and stuff are stored in macros at the top, and then at the end, you can just play around with tweaking them and see if you can grab a few more points just by that. Let's see, bottlenecks. So you'll probably at some point get to a part where either it's the throughput of the util that's killing you more than the other. You'll notice that you're my util is really bad on this guy, or my throughput is really bad on this guy, and that's what's bringing my score down right now. That's what's really hurting me. And so you might want to in the case of util, then you want to think about what design decisions did you make that where you could use memory more efficiently. In terms of throughput, it's often just that something is going slowly. Something is too slow, and that's the reason my performance is bad. And so we talked about gprof last week as a way to figure out what's going slowly. Does everyone remember how to use gprof? You can refer to last week's recitation video if you want to see the demo of it again. It's at the very end. But you can just run gprof on mdriver, and then you can get this list that tells you which function spent how much time, and then you know exactly where it's going slowly. And you might see oh, my coalescing is taking 50% of the runtime, and then you're doing something in coalescing that's bad. Maybe it's your finding a free block. It's taking forever, and then that might influence design decisions to make that faster. Or maybe it's just your implementation of your particular design has a flaw in it, and it's slower than it needs to be. And of course, change the make file back at the end. Otherwise, you'll be compiling with the profiling flag, and that makes things go slower, so you won't get an accurate readout of your throughput. Okay, so some final things. Start now if you haven't started yet. Hopefully you've all started, but it is due Thursday, so if you want to start, come to office hours early. I expect that office hours on Thursday and probably on Wednesday, maybe even tomorrow, maybe even today. They're going to be packed though, and as the week goes on, they're going to be the queue is going to get huge. I know some of you, have been to office hours on the due date before, and the queue just explodes, and it can take a long time to get help. The earlier you come to office hours, the fewer people are there. So if you come tonight, there's going to be fewer people there tonight than Thursday, and you'll be able to get more help more quickly. Make sure you write the heap checker. Write it. Make that a priority to figure out what belongs in that, and to get that written first so that it can help you with debugging. You might have to go back. You probably won't be starting over from absolutely nothing. But be prepared to at points say, okay, I went down this path, and this was actually the wrong path to go down. Maybe I made a bad design decision. Maybe my implementation is buggy, and it's I don't know what's wrong with it. It'd be better to just step back and do it again from a clean slate, more carefully this time. So be prepared, that you might have to regress to an older revision a couple of times as part of doing this. That's not always bad. But think about, you always want to think about, well, why did I have to regress? So that you don't, make the same mistake again the next time. And then before handing in, make sure that you have that header comment. People have been missing that. Still on Shell Lab, some people were missing that. That's worth a couple of style points. It's not hard. So make sure you have that. Make sure you've checked, your line length, your indentation. You can read through the whole style page on the website again and make sure you've got all of that. It's all stuff you want. And then, so any questions? Yes?
You can be more efficient by reading the x86-64 chapter. Is it just reading the entire chapter? Or is it?
Where did it say that? Was that in the handout?
Yes, more than the handout.
Let's see, I'm trying to think. So I'm not actually sure exactly, what part of the chapter it was referring to. So if you read the whole chapter, you'll get the part that it meant for sure. You won't miss it. There's lots of stuff in the textbook that's helpful. Definitely, if you haven't, certainly the stuff about Malloc in the textbook is very helpful, and some of the other stuff around it can help you as well. Any other questions? None? Okay, then you guys can go. Good luck with your Malloc labs.